So I haven't been entirely truthful here. Um, I've kept referring to the double integral as finding the volume, and it does if you have a height function. But there's actually a little bit more that a double integral can do, geometrically speaking. So suppose you have some region of integration between some function f of x and some function g of x, and there's a region bounded. So when you take the the double integral, and you have that same region, so I have some curve here and some curve, I'm running out of space, some curve here, and that same region is here, like that. And this is the x-axis, this is the y-axis, this is the z-axis. Then there's actually some three-dimensional component to that at at z equals 1. So at z equals 1, it would have its compatriot, right? So if I raise this entire thing up 1, right? Then when I take the double integral, I would actually be finding the area. So, right, volume is area of the region R times its height. So if I make it so that the height is 1, then the volume equals area of the region times 1, which means I'm actually finding the area, right? Because this flat disk up here doesn't have any volume, right? Its volume is its area. So the area is the double integral over the region of 1. That's key. And that's going to come back actually in a different form later. So very key to note that if you want the area, you can take the double integral of 1, and that would work because 1 would be your height of this plane. And in other words, this little flat disk doesn't have any volume, so its volume is its area. Nice. All right, so let's use that to find the area of the region bounded by y equals x cubed and y equals negative x squared plus 2x. Okay, so what does that look like? Well, y equals x cubed looks like this. That's y equals x cubed. And then y equals negative x squared plus 2x goes through here. Here, let me do it in a different color or something. So it goes through like this, and then it goes through, it's a parabola, right? So it's going to go like this, and then it touches way down here. I'm not doing a very good job of drawing it, but that's what it looks like. Now, if you're wondering, how do I know that it looks like that? Because I graphed it. Right? So here's what it looks like. So you've got this parabola kind of thing, and then you have the x cubed. So I kind of tried to fix my graph a little bit, but it's still not great. But that's okay. Right? So this is my region right here and right here. Right? So I have two regions. Uh-oh. Right, two regions is going to be tricky because that means we're actually going to have to find the area of both regions and add them up, right? Because we can't do one double integral for this whole thing. Because in this section, the y equals negative x squared plus 2x is higher, and in this section it's lower. So how we would draw the rectangles depends on which section we're in, right? So we're going to draw them vertically, but which one's on top and which one's on bottom changes depending on which section we're in. So this is going to be tricky. So we're going to have to do two sections. All right, so let's call them section A and section B. Okay, so we'll do section A up here, and then we'll do section B down here. Okay, so let's look at section A. Here, let me label this. Okay, so we want the double integral, and we're going to do vertical because these are already y equals and they're polynomials, so it doesn't make any difference which way we go. And since we want the area, we're going to use the integrand of 1. And then since we're going this way, this is dy dx. Remember that a vertical bar is dy dx. So this will be from 0 to when they intersect. So we're going to need to find that intersection. And then dy dx. X is going to go from 0 to when. So we need to know when these are equal to each other. So I used a solve command, and I can see it on the graph as well. It's -2 over here, 0 here, and 1 here. So let's mark those on the graph. So these hit at -2, they hit at 0, obviously, and they hit at 1. Okay, so that's great. So that means that we know it's going from 0 to 1 for our x value. And our y value is going, remember, it's low to high. And on section A, the low portion is the x cubed. And the high portion is the -x squared plus 2. Now, the beautiful thing about integrating of 1 means it's just y. So the integral here is extremely easy. So you say, okay, y from x cubed to -x squared plus 2 dx. So that'd be the integral from 0 to 1 of -x squared plus 2 minus x cubed dx. And of course, we can make Maple do that, or we could do it ourselves. That's a polynomial. It's not that hard, but I'll do it by hand. This is -1/3 x cubed plus 2x minus 1/4 x to the 4th from 0 to 1, which would be 5/12. Because it's 2, take away a third, take away a fourth. So 5/12. So, I mean, if you want, you could say use Maple for that piece. You can use Maple for the whole thing. It's just, this is not particularly difficult. Okay, next, let's do section B. So section B would be the integral from, now that'll be from -2 to 0 for the x. So -2 to 0. And then on this side, the x cubed is on the top, and the -x squared plus 2 is on the bottom. So it's going to be -x squared plus 2, x cubed of 1 dy dx, because we haven't changed the fact that we're doing this vertically, right, with vertical rectangle. Okay, so let's see. This is, again, really easy integral to do. So -2 to 0. This would be y from -x squared plus 2 to x cubed dx, which is -2 to 0 x cubed minus, this is where people get messed up, because it's -x squared plus 2. You either have to put that in parentheses or you have to distribute yourself. So -2 to 0 x cubed plus x squared minus 2 dx. Which again, I could make Maple do it, but this is really easy. So this is 1/4 x to the 4th plus 1/3 x to the 3rd minus 2x from -2 to 0. What's not easy is actually substituting in the 0 minus, right? It'd be 0 minus negative something or other. And then we'd have to put in the 2 and find what it is. Come to find out it's 8/3. Right? Computers and or Maple will do that, and we get 8/3. Okay, so what's the overall area? Let me put that over here. Overall area, it's 5/12 for section A plus 8/3 for section B, which is 37/12. So just to verify ourselves in Maple, here's the plot 3D. And you can see, if I tilt it this way, you can see that that is indeed the region we were looking at. Right? It's kind of small, but it's there. And I'm graphing 1 because I'm trying to look at it up in space, right? So it's at this disk that's at the 1, z equals 1 level. And so when I graph when I integrate the first piece, I get 5/12. When I integrate the second piece, I got 8/3. And together that makes 37/12. So we actually saw 2 key points in this that I don't want you to lose sight of. One is that if you want to find the area, you take double integral of 1 over the region, and that will find the area. That's a big deal right here. And the other thing is that if you have 2 sections, you might have to do 2 sets of double integrals and then add them up. And that's not just true of double integrals. That'll happen in a lot of places, right? So 2 different groups mean 2 different zones, if you will, means 2 different sets of integrals.